Okay.
Yeah.
All right. So maybe let you be the chairman because I have to leave earlier.
Okay, sure. Okay, welcome everyone. And so welcome to this Integrability Journal Club. And this week we are very happy to have Shota Komatsu from Princeton. And he will talk about Wilson loops as metric product states. Let me just say, so as a rule, let's keep all our mics muted, and you can unmute yourself at any time to ask a question. So yeah, please, Shota, it's all yours.
All right, so let's start. So I'm gonna talk about my recent work, my upcoming works with Yunfeng Zhang and Amit Sever and Edward Vescovi. But I also probably mention a little bit about related works that I recently wrote with Yifan Wang and also Joao Caetano, and also 2 related papers which we wrote last year with Yunfeng Zhang and Edward Vescovi. Okay, so let's start. So the plan is as follows. So I'm going to first review a little bit old stuff, which is about integrability on a space of loops based on the paper by Polyakov. And then, well, actually the first part is not really like directly related to my talk, but my work, but I think it's kind of interesting to review that. And in the second part, that's the main part, and I'm going to explain how to rewrite the Wilson loop into matrix product state. And then I'm going to discuss application to circular Wilson loops, and this is mainly about the weak coupling. And then finally, I'm going to talk about how to extend the result to finite coupling using the idea of integrability bootstrap. And then I'm gonna discuss some future directions. Okay, so let's start from the first topic, which is about integrability on a space of loops. So this is basically based on the famous paper by Polyakov in 1979. The title is Gauge Fields as Rings of Glue. So in this paper, Polyakov basically pointed out the relation or analogy between Yang-Mills theory and the Principal Chiral Model. And he was pointing out that Yang-Mills theory can be thought of as the Principal Chiral Model on the loop space. So in order to discuss that, let's first review what is Principal Chiral Model in 2 dimensions. So the Principal Chiral Model, the field in the Principal Chiral Model, so which I denoted by G, lives in a UN group. So it's basically the nonlinear sigma model whose target space is UN. And here, X is the space because I'm considering 2D series, so X lives in R2. And as you can see from here, this G of X is basically a map from R2 to UN. And the action is of the standard form, J wedge star J, where J is given by this Moore-Cartan 1 form, G inverse DG. And if you write it in terms of like a holomorphic coordinates, then it's just the usual like a D squared Z and trace JZ and JZ bar. Okay. And we know that there is an integrability in Principal Chiral Model. And the way to see it is follows. And if you start from that action and derive the equation of motion, and the equation of motion takes this form, the divergence of the current J is 0. And on the other hand, because of the definition, which is J equals G inverse DG, this J also satisfies the flatness condition. And it turns out you can actually combine these 2 different equations into a single equation, and by introducing what's called spectral parameter lambda. And you can actually show basically like by expanding this equation, and then you can actually confirm that it gives this equation and this equation. By the way, this form of like a equation is a little bit non-standard, but you can always do some like a local Lorentz transformation in 2D, which depends on lambda, and convert it into this form, which is probably more familiar to people doing integrability. And where this J mu of lambda is the connection of this form. Oh, by the way, yeah, I think I need some lambda here, but I forgot. But if you put lambda, then it's really the standard form of the lax connection. And starting from this lax, what's called lax connection, you can consider some holonomy. And it turns out because this is really flat, this holonomy actually gives you is a generating function of the conserved charges. And if you expand at lambda going to infinity, then at the leading order, you get the usual neta current, which is J of mu. And the next leading order, you get some non-local current, which is of this form. And all these generators form algebra, what's called the algebra called Yangian. Okay, so this is a standard story about integrability of Principal Chiral Model. Any questions so far? Okay. Now, I'm going to, so what Polyakov did is you can actually reformulate the Amil theory into something that looks like Principal Chiral Model. So the idea is consider this object, G of Cx0. So which is basically just a path ordered exponential. And important point is that unlike Wilson loop, I'm not taking a trace. Because I'm not taking a trace, it actually depends secretly on the initial point of this contour. Because I'm not taking a trace, this G of C actually takes value in UN. So basically this G is a map from a space of loops to UN. So in this sense, it's a little bit similar to G of X, which appeared in the Principal Chiral Model. Now, the Polyakov pointed out that you can actually construct the analog of the connection in this way. So you take G and consider functional differentiation at point X, point S, which is a point on the loop, and then multiply G inverse. So let's see what it means. So if you let's first consider this part. And if you do this manipulation, this is basically like a infinitesimal deformation of the Wilson loop. We know that it inserts this F mu nu X dot mu. So which is the field strength. So this is just like a standard story that infinitesimal deformation of the Wilson loop corresponds to the insertion of the field string. And now you go back and then you multiply G inverse, which is the contour in the opposite direction. And then you can easily see that, for example, this part of the contour can be easily canceled. And then this picture reduced to this picture. So basically, this is just the field strengths transported to this point, starting from this point, using the Wilson loop. And because of this definition, you can easily show that this also satisfies the flatness condition. Okay. So in the case of Principal Chiral Model, there are like two important equations. One is the equation of motion, and the other is flatness condition. So now here we have a flatness condition. So the next question is, what is the analog of the equation of motion? So to derive the equation of motion, let's again consider this representation of J of mu, and then consider this variation. So you deform this like a Wilson loop at point T, which is different from point S here. And if you do so, because these two lines are on top of each other, so there are like two ways of deforming the Wilson loop. One is to deform this part of the contour, and the other is to deform this part of the contour. And that gives you like these first two terms. But in addition, there is a possibility when S is exactly equal to T, you actually like do like a second order variation of the Wilson loop. And this second order variation is just given by this expression. And this is more like a contact term, but what's important here is that this part is exactly proportional, or like it exactly coincides with the equation of motion in pure Yang-Mills theory. So you can basically set this to be 0 if the loop is non-intersecting. But let's just focus on the case where the loop is non-self-intersecting. So in that case, you can just set it to 0. And it turns out the first two terms which survive can be written in this commutator form. This can be easily understood because, like, if you just consider this, well, the commutator consists of two terms, and the first term is like this. So you have like a j of t and then j of s. And you can easily show that this part of the contour gets canceled and this picture becomes this picture. And the similar comment applies to the other term. Okay. Right. So let's write down the equation of motion using this representation for this term. Then I basically get this equation. And starting from this equation, I can further set s equals t. And because we know that even for s equals t, this part is 0 because of the equation of motion of Yang-Mills theory, I basically get this equation. And this is the analog of the equation of motion in the Principal Chiral Model, which was of this form. Okay.
Could I ask?
Sorry?
I have a question. So far as what you described is classical, right? Because even in Sigma model, this is quite hard to quantize this.
Yes,
away
exactly.
From the
So,
classical
so what I'm going to describe in this part is just classical. So I'm just like reviewing what Polyakov proposed. And I think no one really like succeeded in making this into quantum statement. Okay. Is there any questions? Other questions?
So then it's essentially abelian or no. So classical,
it's
what is the limit?
Sorry?
So it could be some non-trivial background, and then
right,
you have
right,
this
yeah. Yeah, it's more about like classifying non-trivial solution. Yeah, even that, I think no one actually did
perfectly non-abelian, of course.
It's non-abelian, yeah. But I think that Collier was pointing out that like in the Principal Chiral Model, classical integrability is used for constructing various solutions. And that might also be true here, but I don't think anyone explored that.
Mm-hmm.
Okay.
So by solutions,
further pointed out that actually in the case of 3D Yang-Mills, you can construct the analog of the Lux connection, which is basically this. So this is the direct analog of the Lux connection for the Principal Chiral Model, but instead of epsilon mu nu, I have epsilon mu nu rho, and that's why I have like a 3D Yang-Mills here. And this is a spectral parameter. And you can show that this d of mu actually commute with each other thanks to the equation of motion and flatness condition. And starting from this, Polyakov also pointed out you can actually construct infinitely many conserved current which satisfies this equation. And the first one is just like a J mu. And the second one is of this form, and where this chi is determined indirectly by this expression. But if you want to integrate it, then in some sense, this involves the integral in the space of loops, because this contains like a differentiation in the space of loops. So this is very abstract, and probably it's not clear what these currents mean. But
so like the purpose, the purpose would be like, say you have some classical background, you want to integrate p exponent along some non-trivial loop, and in principle you can hope that this construction could give you an answer in some cases.
Right, right. Exactly.
Can I just ask, how limited was this to 4D Yang-Mills?
So actually, Polyakov didn't succeed in constructing lax connection for 4D Yang-Mills. So I think this part, up to this part, it also applies to 4D Yang-Mills. But
so I meant, sorry, how about 6D Yang-Mills or 25D Yang-Mills?
Well, that also applies to 60.
Because it's completely classical, right?
Yeah.
But the problem is epsilon with 3 indices, I guess. Right?
No, that
Right.
next one,
so
yeah.
the problem is like how to construct the lax connection. Right. So, okay, so let me try to demystify the meaning of this this current. And this current is basically a one form in a space of loops, much like J mu was one form in the space of R2 in the case of Principal Chiral Model. So in the case of Principal Chiral Model, if you had this J of K, then let's say you insert some operator G of X here, and then you consider the line integral, which is like an integral of star J. And because it satisfies the conservation law, you can basically freely move this contour. And if you move upwards, because you are not inserting anything on the upper half plane, you can shrink this contour and you just get 0. On the other hand, if you move downwards, then this integral acts on G of X and then change slightly. And by doing this, you can write down like an infinitely many word identity. So basically the same comment applies also for
sorry,
this.
when you say, just to get the content, so when you have this contour, there's a contour in the space of loops, right? So it's like a continuous deformation of a loop to itself, right?
Yeah, so it's like a basically infinite dimensional. It's not really, in the case of 3D Yang-Mills, this line is actually infinite dimensional. And yes, what I wanted to say is that you can basically do the same thing, well, at least I don't know how practically you can do it, but conceptually you can do the same thing, and then you can get infinitely many word identities for this loop functional. And of course, like this way.
So what is the analog of time on the right?
There is no analog of time.
It's like having a sigma model where you have some manifold. You can just deform the contours the way you like. So you don't need the real time, right?
Yeah. So this is more like a interpretation of this conserved charges as some topological line defect, and you can like change the shape and then like derive some word identity, and that interpretation also applies to 3D Yang-Mills. Okay, so alternatively, you can also.
Sorry.
Yes.
So one more question. Since it's a loop functional, and the one form, in fact, it's taken in the loop space, I would expect that instead of building a contour or a Wilson loop, you have to build some two-dimensional object. Yes. Sort of a sphere or whatever.
Okay. Right. So here I wrote star J. So the precise meaning I didn't specify, but basically this is like an infinite dimensional object. Like originally this was one form, but I'm taking a Hodge star, which is like taking a Hodge star in infinite dimensional space.
Mm-hmm.
A very massive question. Are you ready? Is the space of loops simply connected?
Unfortunately, I don't have the answer for that. Well, I should say that I just like wrote this just for explanation, and there is actually a much easier way to derive the word identity, which is to just like insert conservation, like a del mu j mu, into the correlator. And that's actually how Polyakov discussed the word identities. So this is just like a picture.
And also, there was always a problem with this scheme because you map the space of loops into the group manifold.
Yes.
Something infinite dimensional into finite dimensional. And
Right.
of course, we know that the space of loops it's very much constrained. It's over constrained. One thing you have functions in the field theory, and another thing you have functionals. So in fact, I think things have stopped more or less on this stage. Nobody understands how to reduce the number of variables.
Right. Yeah, exactly. So that's probably related to the second point, the point that I want to make. And indeed, like as Volodya was pointing out, this map is from like infinite dimensional space to like a finite dimensional space. So in that sense, like it's not very nice. And so but before discussing this point, let me just make a comment that basically this infinite word identity implies some hidden symmetry that deforms the Wilson loops or loop functionals. And in particular, the word identity for the first one is basically equivalent to the loop equation. But there are also problems. First of all, this is established only in 3 dimensions. In particular, for what he mainly talked about non-intersecting loops. But technically, it's important that you have like a co-dimension 1 object. So I don't know if there is any relation, but I just wrote it for curiosity. And furthermore, if you compare this symmetry, infinite symmetry, with the integrability that we know from n equals 4 supermills, it's very different. First of all, he was discussing symmetry at finite n, whereas in n equals 4 supermills, integrability naturally emerges in the large n. And also, his analog of Yangian symmetry, which is like a J mu of k, is an extension of like a UN symmetry. Whereas in n equals 4 supermills, we do have Yangians, but it's extension of superconformal group. And that is kind of related to Volodya's comment. But in the case of n equals 4
can I ask a question?
Yes.
In that sense, wouldn't it be closer in spirit with the stuff that Kevin Costello is doing? There it's more UN, right?
Right, right. It might be.
But then, sorry, you can do the same kind of construction with. All right, doesn't matter.
So actually, I had a related
question. Yeah, if you do it on the sigma model.
First, Kolya, you want to finish?
You disappeared, I think. No, I think Bogdan disappeared. No, I'm done. Bogdan, please ask your question.
Okay. I guess I was going to follow up on the sort of hinting that Pedro was making to Chern-Simons, right? How do I understand? I mean, Yang-Mills in 3D, the coupling constant is dimensionful, the operator is irrelevant. Why am I even looking at Yang-Mills in 3D? Chern-Simons action is much nicer in 3D because it doesn't have a dimensionful.
Yeah. Well, but Yang-Mills confines in 3D, and I guess like there are many interesting physical questions you can ask in 3D. Well, mathematically, I agree that Chern-Simons is nicer, but well, and also probably Polyakov is more interested.
But the point would be that all this loop space description would survive renormalization group flow all the way down to a confining theory.
People discuss the renormalization of these Wilson loops, but of course it's very hard to like go all the way down to the IR. So that's also an obstacle for making this statement into quantum statement. Okay.
But even in the finite dimensional case, in the sigma models, you don't know how to quantize this equation.
That's true, yeah. yeah, directly quantizing is hard. Okay, but I should mention that in the case of n equals 4 supermills, people actually discuss the hidden symmetry of the Wilson loop. And this is actually much nicer. And this is done by, first by these authors and also by these authors. And what they have is similar, but different. And most importantly, they have indeed extension of superconformal symmetry rather than extension of UN. But they are similar in the sense that like they are discussing the symmetry that deforms the Wilson loop. And the first one is the usual symmetry. For example, if you want to write down the special conformal generator acting on the loop, you just need to write this expression, which is just like a direct translation of the usual superconformal transformation. And then they also have some the level 1 Yangian generators, which is basically bilocal on the loop. And they first constructed this at the classical level, and they also discussed the one loop corrections. And so the symmetry of the Wilson loop, which is more relevant to the rest of my talk, is actually this one. So that's why I said in the beginning that work by Polyakov is not directly relevant to my talk, but anyway, I thought it's kind of nice to review that. All right, so, but I should emphasize that this nice hidden symmetry, the relation to the usual integrability of local operator was not fully understood. Well, of course, like you can guess some relation. But let me just say, for those who are not familiar with the integrability of the local operator, let me just say that the idea is to consider a single trace operator, let's say made out of two complex scalars and z and x, and then map z to upspin and x to downspin. Then people found, basically Minahan and Zarembo found that the dilatation operator at one loop can be identified with the nearest neighbor Hamiltonian of the Heisenberg spin chain, and which is known to be integrable. So you can actually diagonalize this dilatation operator using the technique called Bethe-ansatz.
Could I come in here? So it's like in the case of fishnet, right? So we need to add some where actually all this Yangian was acting on the analog of Wilson line. Of course, the Wilson line is a bit degenerate, like trace of scalars sitting at different points. But if you kind of map it back to n equals 4, this would be kind of a Wilson line. And then the graph building operators and all other charges commuting with that, they would like constitute Yangian in the same way.
Yeah, I guess that's indeed a very nice place to study what I'm going to talk about indeed.
Like what we call CFT, I mean, Amit is a big fan of this name, CFT wave function, and which is a correlator of local operator with this kind of open and scalars, or you can also interpret it as a Wilson line, Wilson loop.
Right, yeah. Yeah, well, actually I might make some comments at the end of my talk, but I guess Kola will not be here when I make that comment, but anyway, so is that
a nice comment, then I may stay.
Sorry?
That's a nice comment, then I may stay.
All right, so this is the end of the part 1, and the goal of the part 2 of my talk is basically to explain one setup in which you can actually relate the integrability of local operators and the integrability of the Wilson loops. Okay, is there any questions so far? Okay, so let's start the second part, which is to rewrite the Wilson loop into matrix product state. So in order to do that, there are two key ideas. So first, instead of just discussing the Wilson loop, I'm going to discuss a correlation function of a local operator and the Wilson loop. And the second important point is to consider, instead of fundamental Wilson loop in the fundamental representation, I'm going to consider our generating function of the Wilson loop, which is of this form. So W is the path-ordered exponential, and I'm going to consider this object, and A is something like fugacity. And if you expand this expression, you get 1 at the leading order, and then in the next order, you get a usual Wilson loop in the fundamental representation. And at the next to next leading order, you get a Wilson loop in the rank 2 antisymmetric representations. So this is a generating function of all the antisymmetric representations of the Wilson loops. So both of them seem like unnecessary complication because I just wanted to understand the Wilson loop in the fundamental representation. But the goal of my rest of my talk is to convince you that these are actually necessary generalization in order to really understand the fundamental Wilson loop. Okay, so let me first discuss the first point. So I said I'm going to discuss the correlation function between Wilson loop and local operator. So for instance, I put local operator here and consider Wilson loops around it. And the first comment I want to make is that because my objective is to make connection between Wilson loop and local operator, it is actually a very natural object to consider. And the second comment is that if the Wilson loop is straight line, then because n equals 4 superMOs has a conformal symmetry, it's related to some defect CFT data. So it's basically bulk defect 2-point function where the defect operator is the identity operator. And the third comment is that this is a nice object which relates UV and IR physics. So let me expand a little bit this comment. So this relation between UV and IR is most visible in the confining gauge theory, not necessarily in n equals 4 superMOs. So what I mean by this is that we know that Wilson loop is a nice order parameter for confinement, especially if you consider very large Wilson loop. So it's an order parameter that distinguishes the IR phases. And for instance, if you consider Wilson loop and take area to be very large, then in the confining phase, you get the area low, whereas in the deconfined phase, you get the perimeter low. On the other hand, operator O is defined at a point, and it's a kind of natural probes of UV physics. And in this sense, like the correlation function of W and O is something that relates UV and IR physics. And you can also see that in some holographic picture. So let's say you consider some kind of confining geometry. And typically confining geometry looks like ADS near the boundary of the geometry. And in the IR, it gets capped off and becomes this kind of flat metric. And if you consider a very small Wilson loop, then the typical surface which connects the operator and the Wilson loop is like this. But if you consider a very large Wilson loop, then it stretches all the way down to IR and comes back. And in this sense, like by changing the size of the Wilson loop, you can explore more and more the space inside. So this also shows that like this is a nice object which proves UV and IR. And also from the worksheet picture, if you consider some local operator here, then the typically local operators are made out of some fusing of the gauge theory, and this correlator can be thought of as some kind of like a measurement of these like individual excitation contained in the operator by the IR detector, which is a Wilson loop. So in this sense, it also measures the UV and IR physics on the worksheet. All right. So let me, having given this comment, let me just explain more in detail the setup that I'm going to consider. So as I said, I'm going to discuss this generating function. And in particular, well, let's for simplicity consider what's called locally BPS Wilson loop, which couples to gauge field and also to scalar field. And the same comment applies here. And if you expand it, then you get like a various different representation. And if you want to get a particular representation, you can just do the integral over A and then project it to a case antisymmetric representation. And also below, I set theta I, which basically determines the direction of the scalar coupling to be 1, 0, 0, 0, 0 for simplicity. Okay, so this is the setup. And I also want to specify what kind of operator I'm going to consider, just to be more concrete. So the operator that I'm going to consider is the operator called SL2 sector, which is basically the operator made out of complex scalar and one covariant derivative. So this complex scalar, I take it to be phi1 plus I phi2, and this covariant derivative is d0 plus d1. And I assume the Wilson loop is living, for instance, here, and this covariant derivative picks one direction from this plane and picks one direction from the orthogonal, one direction orthogonal to this plane. And this operator is also known, it is known that this operator can also be described by some spin chain, which is called SL2R non-compact spin chain. So the only difference is that in the case of usual Heisenberg spin chain, you only have up and down. So basically there is only one kind of excitation. But here, like a excitation or magnons can be on top of each other. So they are labeled by integers. So, and also in the rest of my talk, I'm focused on free n equals 4 CPM but interaction can be included perturbatively. And another comment is that many things apply also to non-SUSY Wilson loop and other theories, but in my talk, I'm going to focus on n equals 4 CPM just to be very concrete. Okay. So the way to convert Wilson loop to matrix product state consists of 4 steps. And actually, this is exactly the same 4 steps that I used in my previous papers on the determinant operators, the correlation function of determinant operators. So step 1 is to express this generating function as a passive integral of the 1D fermion. So the idea is that you take this expression and then write it in this way. And this chi and chi dagger is a 1D fermion. It's a fermion living on the Wilson loop, and its action is given by this expression. So, and chi is a fundamental representation of UN, and chi dagger is anti-fundamental representation. So the chi lives on the contour of Wilson loop. And this representation was actually rediscovered many times in the history. And I think like the first one is around 1970. Well, I don't even know like which paper actually first pointed out this equality. But the one I personally like is the paper around 1990, whose title is a topological field theory approach to non-abelian Stokes theorem by Broda. So you can actually get, I think, read it online. And so the reason why I like it is he actually further reformulated this 1D fermion into 2D theory, like a fermion living on the 2D surface, bounded by the Wilson loop. And it does seem a bit like a string worksheet. Okay. So this is a step 1, but let me just explain why this equality is true. To understand this equality, it's better to go from passive integral representation to the Hamiltonian representation of this 1D system. So if you do the canonical quantization, because they are fermion, like they satisfy this anti-commutator relation, and this passive integral, you can actually rewrite it in this way. where n of chi is just the number operator of this fermion, where this h is this. So you take this gauge field, and A is basically like a label for the generator, UN generator, and then you couple it to the bilinear fermion. Okay. And the point here is that if you look at this operator, which is the bilinear operator of this fermion, and then act it on the k fermion states, first of all, I should point out this, because they are fermion, these indices, which are UN indices, shouldn't be the same. So this already looks like antisymmetric representation. And what's nicer is that if you actually act this generator on this state, then its action is exactly the same as the generator in the case antisymmetric representation. So this basically says that this trace can be decomposed into like a k fermion sectors. And for each sector, you can regard this as the trace of the path-ordered exponential. And the trace is taken in this like a case antisymmetric representation. And I also get this e to iak coming from this e to ia and chi factor. Is there any questions so far? Okay. So this is a way to rewrite the Wilson loop or generating function of Wilson loop into a fermion. And there is actually also a string theory interpretation or construction, which is discussed by Gomez and Passerini.
So sorry, could we look a bit longer on the previous, just to
sure,
digest? Yeah. So when you say H acting on what? How does it act on?
H acts on the space of fermions. So TAs are just like a fixed matrix, like a C number matrix.
And this coefficient in front is just a C number.
Yeah, this coefficient in front is also C number at this level.
Okay. Yeah.
Okay, so let's go. So there is also like a string theory construction of this story, which was discussed by Gomez and Passerini. And basically, they pointed out there is actually string theory interpretation of these fermions. So the point is that in the case of n equals 4 sup m mils, you can actually construct this generating function of the Wilson loop by considering intersection between n D3 branes and one probe D5 brane. And if you consider this setup, then there is an open string stretching between D5 brane and D3 brane. So this open string contains one index from D3 brane. So it's going to be something like a fundamental representation or anti-fundamental representation. And indeed, if you work out what is the lowest lying modes of this configuration, you discovered indeed like you get a fermion. So this is really like a string theory interpretation of this chi and chi-Derger. So it's basically just the open string. And if you use the ADS CFT correspondence, then it amounts to replacing this ND3 brane by ADS geometry. Then it really becomes a probe D5 brane inside ADS spacetime.
Sorry,
Okay.
Is that the open string has got 4 Neumann-Dirichlet boundary conditions?
Right. I think that's right.
So 4 rather than 8.
Yeah.
So there are bosons as well as the fermion in the multiple.
Okay. Yeah, I always get confused, but
there are dn directions. So it's one end ends on this brane, one end is on the other brane.
Right.
Yeah, but how many? It depends. 4 or 8. Those are your choices. I assume you're not breaking supersymmetry.
No.
And if it's 4, which it looks like, then there should be bosons as well as fermions. Maybe I'm wrong. Maybe it's 8.
No. I think it's 8 because the intersection is one-dimensional. You have 4 plus 5 minus 1.
Okay.
Mm-hmm.
I see.
Mm-hmm. Oh, right.
I
Yeah,
see.
that's right. Thanks.
Thank you.
There is also another configuration, which is a D3-D3 intersection, and that is probably 4, and that is related to symmetric representation.
Indeed, yes. Okay, so now we succeeded in rewriting Wilson loop in terms of fermion, and the next step is to integrate out n equals 4 supermills. I'm going to do it in the free limit, as I said, and so in order to do that, let's write the combined action of n equals 4 supermills and the free fermion and the fermion. So the fermion has this part, and also the n equals 4 supermills has this part, and there is also a coupling between fermion and n equals 4 scalar field. So originally I wrote it in this way, so which is like a this representation, but I like rewrote it in this way. Trace of phi chi chi. Is this point clear? Okay, so now because I'm going to work within free theory, I can just integrate out scalar field. Of course, I should also integrate the gauge field, but let's first focus on integrating out scalar field. But this is of course easy. Well, I just have some source term coming from fermion, and I can always do the Gaussian integration. And basically, technically, in order to perform the Gaussian integration, you basically do you complete the square. So you shift phi by phi classical, and then compensate unnecessary term by this. So let me just be more precise what I mean by this. So I wrote this expression, and where phi classical is designed in such a way that I reproduce this in original Lagrangian. And in order to do that, you need to have this expression. And from this, it's clear that this part is quartic in fermion because I have like a chi dagger here. And now after this rewriting, I'm just going to integrate out this phi minus phi classical because now it's decoupled. But if you do so, so this amounts to like a splitting phi into phi minus phi classical plus phi classical and integrating out this piece. Then, so if you do so, then you need to remember that there is also operator insertion. And for the operator insertion, this amounts to replacing phi in the operator with phi classical. Because I split it into 2 parts and then I integrated out the rest. All right, so this, right. So this is what you need to do the operator. So now let's look at this. So if I integrate out, then this part is gone. So I'm left with this part. And as I was saying, this is quartic in fermion because each phi classical contains like a chi here. And importantly, each phi classical contains integral of tau. And if you combine, then you see that this is the action that you get. So this is actually non-local quartic action of fermion. So you have like a 2 integrals. And this term is precisely actually the propagator of the scalar field. So roughly speaking, what is happening
sorry, can you summarize which approximation is no interaction in the bulk?
Yeah, so I'm just using the free Mills action.
Mm-hmm.
But it's actually important point because even if you take free Mills, the Wilson loop can self-contract. Like for instance, like in the case of half BPS Wilson loop, people often talk about rainbow diagrams. That's already within free theory. Okay, so.
But there, so magically it extends beyond free theory, right?
Right. So as I was saying, so this is a non-local and quartic action of fermions. And so far I was doing the integration of the scalar field, but if I include a gauge field, I just need to replace this with a combination of the gauge propagator and the fermion propagator. And this becomes this expression. Okay. So now step 3, which is very simple. So now I have like a coordinate interaction of fermion. And so the standard way to analyze this kind of coordinate interaction is to use the Hubbard-Stratton-Witz transformation. So the idea is to integrate in some extra field, which I denoted by rho, which corresponds to chi-Dagger chi. And importantly, this is by local field. And you can easily show that this, by integrating in rho, this action becomes this action. And you can also go back to in this way by integrating out rho. So here I denoted this part by y.
Sorry, but do you have in mind some 2D Young-Mills localization type of picture, and or not yet?
Not. Yeah. So I'm just saying that this is the way to do the computation in the free approximation, and then I can systematically include the loop correction. But okay, as you are pointing out, in the case where operator is BPS, sometimes this computation becomes exact. Okay, so this is the action that you get. And now the next step is obvious because I only have like a Gaussian action for a fermion, so I can integrate out fermions. So I take this expression and integrate that. Then obviously I get fermion determinant, one loop determinant, but because I have like n fermions, because they are fundamental or anti-fundamental, it's actually determined to the power n. And if I write it in terms of exponent, then it's like a minus n times trace log of this object. So now we are in a good shape because we have n here and also n here in this quadratic term. So everything in the exponent is proportional to n. So I can analyze everything using the saddle point equation. And the saddle point equation is precisely this equation. Okay. All right, so, but I also still need to remember one thing. So, because I was not just considering the Wilson loop, I was also inserting the operator. As I was saying, after the first step, you replace phi with phi classical, which is like a bilinear fermion. So yeah, I wrote it in this, explicitly. And then if you integrate out fermions, I also need to do the weak contraction fermions. But it turns out in the large n limit, this weak contraction is very simple. Basically, you just need to weak contract the neighboring fermions inside a single trace operator. So the reason is, if you look at the propagator of the fermion, there is a delta function of the color indices. And if you contract the neighboring fermions, then because of the matrix structure, these indices are same. So you always get delta AA, which produces a power of n. Whereas if you connect it in a different way like this, then you don't get that power, that factor. So the leading large n answer is just given by this like a nearest neighbor contraction. And then, of course, whenever I do the contraction, I need to put this propagator factor. Okay, so now let's see what I got. So I do the weak contraction and then I get this expression, this propagator factor. And in addition, I should remember that there was also this factor. Well, here I just wrote the fermion part, but there is a integral of tau and also this prefactor. And this prefactor is important if the operator is differentiated, because in that case, I need to insert this factor. And in particular, for operators in the SL2 sector, if you do this manipulation, then you find that the correlation function of the Wilson loop in the local operator is given by this expression. So you have like a L tau integrals, and this you can think of it as a kind of like a functional trace, where each m have two indices, which is continuous, like tau and tau prime, and given by this expression. Okay. Any questions?
So how does it reduce to some finite dimensional cases which are no, or it's too far away?
You mean finite dimensional matrix?
No, okay, so yeah, so it's okay, that's fine.
Yeah, it's always infinite dimensional, like regardless of the representation. But yeah, okay, but let me just make some comments.
You're looking in the previous slide only on the non-compact integrable structures, right?
Mm-hmm.
So this is why, and those when you take this by local combinations, you are looking, on the operatorial insertions, you are looking only exception on the nearest contractions, right? So you haven't added any loop contributions or something. I mean, in the O insertion.
You mean O insertion? Okay. O insertion, I only considered SL2 sector. Yes, is that what you're asking?
Yeah.
Right, but actually, this structure is true even if you consider like a SO6 spin chain sector, because this infinite dimensionality is coming from the Wilson loop, not from the operator.
Okay. Yes. Sure.
Right. So I have this expression, and yeah, and I have this expression, and pictorially you can understand each part of this like a matrix as in this way. So you have operator and the Wilson loop, and you are doing the weak contractions, and then there is some propagation of the fermion fields, which is this form, this part, and then whenever this fermion gets hit by this propagator, it spits out this factor, because this propagator comes with some derivative. So it depends on how many derivatives you put. And alternatively, you can also express this as an inner product between matrix product state and the operator. So this is just a trivial rewriting, basically. So instead of like just looking at this particular operator, I just consider sum and then express the correlator as the inner product. So let me make some comments. First of all, so this is indeed the matrix product state, but it's a little bit weird matrix product state because the bond dimension is infinite and furthermore continuous. But you can also convert it into a discrete infinite matrices by doing the Fourier transformation. So basically I have like an integral starting from 0 to 1, but you can just convert it into Fourier modes.
So sorry, can we think about coffee break at some point?
Right,
What would be the natural?
Yes, this is precisely the point I want to make coffee break. And this Fourier decomposition is also very nice for the BPS loops. And this is precisely a good point to stop.
All right, so yeah, we continue in 10 minutes, but I leave you alone.
Okay, please, Shota.
Okay, so let's continue. So now, so far I was discussing general locally BPS Wilson loop and explain how to rewrite it into matrix product state. But so far I didn't do any explicit computation. So now I'm going to do some explicit computations and make some connection to integrability. And in particular, I'm going to focus on circular loop, which is known to be one half BPS. So there are some simplification if you consider circular loop, which is half BPS. So let me remind you that the formula that I got is given by this expression. It's the overlap between MPS and operator R, and the MPS is given by this expression, where M is infinite dimensional and given by this expression. And this rho is determined by the saddle point equation, where Y is some propagator between 2 points on the Wilson loop. And what is nice about the circular Wilson loop is that if you consider the circular Wilson loop, it turns out that Y is just constant. So this equation simplifies a little bit. Furthermore, because of the symmetry of the Wilson loop, we expect rho of tau tau prime to be dependent only on the difference tau minus tau prime. So therefore, you can easily expand rho into the Fourier series, and where n runs from minus infinity to infinity. And the shift by 1/2 here, because rho was originally the bilinear of the fermion. So rho is a Hubbard-Strantanovich field I introduced for bilinear fermion. And because it's fermion, so the periodicity is actually like there is some -1 sign. So that's why I need to put 1/2 here. So now, using this Fourier model expansion, you can write the saddle point equation in this way. So like everything can be decomposed into Fourier modes, and you can actually solve this equation. And the exact solution is given by this expression. And I should emphasize that this square root plays a very important role. Now, I just plug in that expression into this matrix product state. And in particular, if I focus on particular SL2 sector that I introduced earlier, and furthermore, insert the operator at the origin, I get this expression, this explicit expression for the circular Wilson loop. And it turns out, so this matrix itself contains n, but its dependence on tau is now simple because you just have exponential and you only have cosine here. So it turns out, so this trace, functional trace, which involves multiple tau integrals, can be converted into sum over ni's by performing explicitly tau integrals. And then you get a representation of the matrix. Now it's a discrete infinite matrix, and the matrix element is given by this expression. So now I'm performing explicitly the integral of taus. So this is a simplification you get for the circular Wilson loop. And in particular, if you consider the trace of Z to L without any covariant derivatives, that amounts to setting SI to 0. And that is very simple, because if I set S to be 0 here, I only have exponential 2 pi I tau n minus n here, which basically means that this matrix is diagonal. Because it's diagonal, it's very easy to take a trace. It just reduces to like a one sum, and you have like a power to L. And this infinite sum can be further converted into integral using the usual Sommerfeld-Watson trick. So the idea is to consider some function, which is this function, which is posed at these integer points, and then rewrite this infinite sum into integral and deform the contour and encircle some branch cuts in the integrand. And importantly, because rho n contains some square roots, there is actually branch cut here. And after appropriate transformation of the variables, it boils down to this expression. So this 1 over XL is directly coming from here. And this tangent hyperbolics is precisely coming from the Sommerfeld-Watson transform. And it turns out this actually reproduces the localization result, which was computed earlier using the matrix model. Okay, so in this particular case, so the approximation that I did was actually exact because of the supersymmetry. So And once you get the result for this trace of Z to L, you can also get the expectation value of the Wilson loop. So the idea is to set L equals 1. So we know that in SUN theory, there is no operator with L equals 1. But if you compute this quantity in the UN theory, the answer is non-zero. The reason is precisely because in U1 theory, there is a correlator. So this result for UN theory factorizes into the Wilson loop expectation value in SUN theory and this correlator in U1 theory. And because U1 theory is trivial, you can easily compute this. So, and then by dividing this by this factor, you can actually extract this Wilson loop expectation value. And another comment is that if you want to project the fundamental representation, you can simply do it by doing the A integral. And you can do it at the level of this integral of x, and that gives you this expression. And if you evaluate, this gives you Bessel function. And if you further set it to 1, you get the famous result for the circular Wilson loop, which is like a Bessel 1. Okay, so this was application for
Sorry,
the BPS.
Shota, can I ask?
Yes.
So what happens? Why don't you get identity if you set L to 0? Or would you expect to get?
L to 0, I think you get 0, just
Okay.
because there is no operator. Yeah. Well,
so is well, okay.
Yeah, well, I don't have a clear-cut answer for that, but yeah, indeed, I was also originally expecting maybe setting L equals 0 gives you the right answer, but it seems like there is some subtlety in setting L equals 0 because I just get 0. Okay, so now so far I was only discussing the BPS operator, but of course the main goal is to understand the correlation function between non-BPS operator and the circular Wilson loop if you want to make connection with integrability.
Also, sorry, Shota,
yes.
Another question. Sorry. Can I ask you to comment on the similarity of the result with the boundary case or the interface? It's very similar, right? To the previous result, the one-point function with the interface.
You mean localization result? This result?
Yes.
Yes. Yes, in the right.
Yes.
So we recently computed the one-point function in the presence of defect, codimension 1 defect. In that case, you basically, for k even, I think, so there is a label k, which labels the defect. For k even, yeah, I indeed get almost the same integral with a set to 0. But in addition, there is some sum, like a discrete sum term, which is like a 1 over, well, sum over 1 over x to some power. And so indeed, the result looks very similar, but it doesn't coincide. Okay, so well, I will make further comparison when I talk about integrability. So for SL2 sector, we basically used our matrix product expression and performed computation by Mathematica for various different states or various different operators. And we found two interesting things. The first thing is that this overlap is non-zero only when the magnons, so these are like magnons of excitation in SL2 spin chain. So rapidity or moment of excitation of SL2 spin chain. So the overlap is non-zero only when the rapidity is parity symmetric, like a set of rapidity is parity symmetric. The same structure was also found in the defect one-point function by Kostya and Charlotte and their collaborators. And we now understand that this is basically implying that MPS has some hidden symmetry, and it can be thought of as some integrable state, integrable boundary state. So the second thing is more interesting. So what we found is that now we did the computation for the SL2 sector, and we got some number. And initially, we didn't understand what those numbers are, but then we finally figured out it can be expressed in this way. So there is some integral which involve what's called Q function, which is just a product of this factor where UK is a rapidities, and then times some Gordon-like determinant. So let me explain a little bit about this expression. And so this is the expression that I got, that we experimentally found.
So Shota, sorry.
Yes.
You hear me? So this matrix product state, you say it's integrable. Of course, it has a pair structure, right?
Right.
So so can you show that is annihilated by some charges or?
Well, I think it's possible, but technically it's a little bit hard.
Okay.
We are trying it right now, but technically it's a bit hard because precisely because like the bond dimension of the matrix is infinite.
Infinite, right. Right, and so it should be also difficult to show that this matrix product state is some kind of a eigenstate of some spin chain or something. Normally, these matrix product states can be thought of as initial states, which are, of course, some kind of eigenstate.
You mean like in the context of quench?
Of quenches, right, exactly, that's true.
Well, right, but you can still use it as the initial state
right,
without
of course.
specifying.
No, this, yeah.
What the Hamiltonian
would be interesting to know if it's a spin chain.
Well, this is definitely a spin chain state, but so you can definitely use it for the quench analysis. Right. So the comment that I wanted to make is that so this is a result for the generating function. And for the fundamental representation, again, I just need to do the integral of A. And if I do the integral of A, and I just replace this tangent hyperbolic factor by exponential. And this formula is very interesting because it's in some sense a hybrid of localization and integrability. So let me remind you the localization result for BPS operator was of this form, which precisely contains a similar factor. But it doesn't contain, of course, these Q functions. And it also resembles the defect one-point function studied by those people because it basically contains the same determinant, Gordon-like determinant. If you're curious, this is the explicit expression. So now the question is why this formula looks like a hybrid of the two. And explaining that is the part for my talk.
Sorry, Shota? Usually,
yeah.
You usually get the ratio of determinants, G plus or G minus.
Okay, yeah. So, well, because I was not normalizing by the norm of the state.
Oh, I see.
It's precisely the same. Basically, this determinant structure is precisely the same. I'm just not normalizing it.
Sorry, another question. In this integral, do you pick up the poles at the zeros of Q of U? Or which poles should you pick up?
Sorry, so this integral is around U equals 0.
Ah, okay.
Okay, so let me see. Okay, let me make a quick. Okay, well, I can skip here. Yeah. So let's directly go to the bootstrap story. I can go back to. So this is more like a future direction. So I can go back to it at the end of my talk. All right. So now let's discuss so far I was doing some perturbative computation, and let's discuss how to uplift to a finite coupling. So the idea is to use intuition from the worksheet, string worksheet. So this correlation function between the Wilson loop and local operator corresponds to a disk amplitude with one puncture insertion. So you have some like a disk string worksheet where the boundary is ending on the Wilson loop, and you have one closed string vertex operator insertion, which is dual to the operator OR. And this expression can also be converted into this form by just doing the conformal transformation. So you have operator state OR corresponding to the closed string, and you have a boundary state B corresponding to the Wilson loop. So in this sense, you can view this as the overlap between the boundary state and the closed string state. So now the goal is to determine this boundary state, sorry, I should have written B here, at finite to foot coupling using the idea of integrability bootstrap. Okay? But before doing that, let me make comments on other observables that are also described by the similar worksheet. So there are by now, well, two well-studied examples. One is the three-point function of two determinant operators and one single trace operator. And on the string theory side, these two determinant operators create some geodesics of D-brane in ADS spacetime, and you're attaching a closed string to it. So that's why it's also described by the disk with one puncture. And another setup is precisely the setup studied by Kosha and Charlotte and Marius and other collaborators. And this is the one-point function in the presence of domain wall. So the idea is to consider D5 brane intersecting a stack of D3 brane. So on this side, you have just n D3 brane, and on this side, you have n plus k D3 brane. And what is happening here is that k by k matrix of this n plus k plus n plus k matrix coming from this part gets a vev. And that's why you only see like a SUN gauge symmetry. And in both cases, if you do the computation at pre-coupling, you discover that both can be expressed in terms of matrix product state. So in the first case, you discovered, well, we discovered actually that it can be expressed in terms of matrix product state with bond dimension 2. Whereas in this case, because you are giving a vev to this k by k component, you have a matrix product state with bond dimension k. So now we have a matrix product state with infinite bond dimensions. But apart from this difference, the worksheet looks very similar. So we expect the same strategy should work here. So what is the strategy? So the idea is, okay, so the first step of this program is to interpret this selection rule that I mentioned earlier. So this overlap is non-zero only when beta roots are parity symmetric. And thanks to the work by Goshel and Zamolodchkov in the context of relativistic field theory, and also the work by these people, Piroli, Poshka, and Vernier, for integrable spin chain, we know that this selection rule basically implies or means that the state B is integrable boundary state, which is annihilated by odd higher spin charges. Well, precisely speaking, I think what they showed is in this direction, not in the other direction. But basically, from these works, like it's very likely that once you see this selection rule, this should be the integrable boundary state. And nice thing about integrable boundary state is that if you take the limit where the spin chain is very large or the operator is very large, then we expect this decomposes into the two-particle overlap. So now the question boils down to determine this like a two-particle overlap. And you can do so by imposing various consistency conditions, symmetry, Watson equation, boundary and Baxter equation, crossing equation. And once you do that, you can actually write asymptotic formula that captures all the perturbative 1 over L corrections. And after that, if you also want to understand the non-perturbative correction, non-perturbative in length of the operator, then you can use what's called exact G function using TBA, thermodynamic beta inverse. But I'm not going to talk about this part today. So now, so what we need to do is basically do this step 2, mainly using the consistency condition to constrain this overlap. And the first constraint is this, the symmetry. Basically, the symmetry means that you pick some generator in the symmetry group and insert it, and it should be 0. So this is just a standard word identity. But in order to do that, we just need to identify what the symmetry group is. In this case, it's very simple. First of all, because you're inserting a local operator at the origin of the circle, it is invariant under U1 rotation of this plane. It is also invariant under the U1 rotation, which rotates orthogonal, the plane orthogonal to these two planes. So because we are in 4D space-time, so you have like extra two planes. So in addition, you have SO4R symmetry. And if you further include the fermionic symmetries, it turns out that the symmetry becomes SU1/2 squared. Let me just comment that in the case of defect 1-point function, the symmetry was SU2/1 squared, well, which is basically the same, but like the roles of R symmetry and the space-time symmetries are swapped. Whereas in the case of determinant 3-point function, it was diagonal SU2/2. Okay, so in order to use the symmetry analysis, there was technical ambiguity, which is related to what people call Z markers. This is related to the fact that if you perform a supersymmetry transformation to the fermion field in n=4, then it actually increases the length of the spin chain because it spits out this Z. And in order to use this symmetry as a constraint, you need to know how to relate this overlap with extra Z insertion with the overlap without extra insertion of Z. And to proceed, we basically just assume that it's given by some factor, and I parameterize that factor using this Joukowsky variable. And later, it turns out that this A is precisely the fugacity parameter contained in the generating function. But this was just a technical comment. But now, so this was the symmetry constraint, and I can also use the Watson equation, which is basically saying that this overlap between boundary state and then two particle states is invariant under the action of the S matrix. And there are also some other constraints coming from integrability. So one important thing is what's called boundary Yang-Baxter equation. So, well, let me not explain the detail and just show the picture. So this is a picture of the boundary Yang-Baxter equation. So this is like a boundary scattering analog of the usual Yang-Baxter equation. And in the context of n=4 Mill theory, recently it was analyzed in detail by a nice paper by Zoli and Tomas. And I guess like we'll hear more about it in 2 weeks. And in addition, there is what's called crossing symmetry, which is basically saying that if you add a particle and antiparticle pair, it must decouple. I'm not going to tell you how to solve it, but if you solve it, you find this expression. You have this factor and some complicated factor. And now if you look at this factor, then you see that there is a pole at u = ±a ± I/2. So this is meaning that this actually has a physical meaning. So this means that, so typically if you have a pole in the S matrix, it means that there is a bound state. Here, if you have a pole in this overlap, it means that there is some bound state between boundary state and the bulk particle. And that bound state can be thought of as some excited boundary state. So I started from one boundary state, but then discovered that there is also another boundary state, which is some kind of excited boundary state. And what's nice about this integrability setup is that this overlap for the excited boundary state can also be determined by the bootstrap analysis. So there is a bootstrap relation which relates the overlap for the excited boundary state with the overlap with the original boundary state. You just need to move, it's basically saying that you can move this part to here. And if you do so basically what you need to do is to multiply two S matrices to the original overlap, and that gives you the excited boundary state. And if you do so, you get this factor. Now you see a new pole at a plus 3i over 2. And you can actually repeat this infinitely many times and discover infinitely many excited states, excited boundary state. So this is really like a manifestation of the bond dimension of the matrix product state. So at weak coupling, we discovered that we had a matrix product state with infinite bond dimensions. And here we discovered that we have excited boundary states, and the number of excited boundary states is infinite. And this relation was actually also true for the defect one-point function. And in that case, we had a k-dimensional MPS, and indeed we discovered the k excited boundary state. Okay, so then the final asymptotic formula is given by sum over all these excited boundary state contribution, and which are labeled by integer, which runs from -infinity to infinity. And because you have infinite sum here, you can again try doing the Sommerfeld-Watson trick. And if you do so, finally, you get this kind of expression whose weak coupling limit precisely reproduces what we found using the perturbation theory. Okay, so this was a bit quick, but this was basically this, how you can uplift what we found at weak coupling to finite coupling using the idea of integrability bootstrap. But let me make some comments. So first of all, again, so far we are discussing, so we had distance, and that's because we are discussing the generating function. But if you want to get the fundamental representation, again, you just need to do the integral Fourier transformation. And then that basically converts this tangent hyperbolic into this exponential. But I should emphasize that for this tangent hyperbolic, we have a clear physical interpretation. This is basically just coming from Sommerfeld-Watson. Whereas here, we don't really have physical interpretation, because now all the poles which are originally in the tangent hyperbolics are gone. So if we were only discussing the fundamental representation, it's very, very hard to justify why we are getting this factor. It's only because we started with the generating function, we understand why this tangent hyperbolic factor comes from. So another comment is that, again, the structure of, there is some very deep relation between the structure of MPS at weak coupling and bootstrap solution at finite coupling. In particular, the number of excited states is related to the bond dimension. And furthermore, there is a bit weird feature that if you consider BPS operator, this Sommerfeld-Watson trick basically gives you the exact answer. So somehow this asymptotic formula, which were supposed to capture only like a perturbative 1/L correction, seems exact in this case. So this is a bit weird, but if you have any question, I can explain a little bit more about it. But for now, let's just end the talk by discussing the future directions. And so there are several future directions we can discuss. One possibility is to use this MPS representation as some intertwiner, which relates the integrability of the local operator and the Wilson loop. So the idea is as follows. So now we know that the correlation function between local operator is given by this overlap, and this MPS is a functional of the contour of the Wilson loop. Now, suppose you insert some Q operator, which is some operator which is a kind of generating function of concept charges into this overlap. If I act Q operator on this side, I just get some number, well, some function, because this is the eigenstate of this Q operator. Whereas if I act Q operator here, I modifies the MPS. So we know like how it modifies because we know how to write MPS as a spin chain state. So now, interesting question is, can we understand this small deformation on MPS as coming from a small deformation of the contour? In principle, we have expression for MPS for general contour. So in principle, I think this is doable. But once you can do it, then you can possibly relate the integrable structure of the spin chain and the integrable structure of the Wilson loop. And in particular, this implies that there should be some deformation of the Wilson loop, which satisfies QQ relation, which is the relation satisfied by the Q operators. You can also insert Yangian instead of Q operators. And then you may be able to relate the spin chain Yangian and the Wilson loop Yangian discussed by Kostra and his collaborators. But there is some little puzzle, because we know that the spin chain Yangian is broken by the cyclicity, whereas Wilson loop Yangian they constructed is actually unbroken by the cyclicity. So there is some mismatch. I don't know what this match is telling us. Maybe it's telling us that what I just said doesn't make sense and you cannot write the deformation of MPS as a deformation of the contour. Or maybe you can be optimistic that there might be some new spin chain Yangian, which is not broken by the cyclicity. And also, like there is an interesting question of whether we can promote this idea to finite coupling. We don't know how to promote Q operator to finite coupling, but we do know how to promote Q functions to finite coupling, which is precisely quantum spectral curve. So another interesting avenue is that like maybe this gives you a way to find a new integrable Wilson loops. So as I was saying, we basically have a representation for MPS for generally BPS, locally BPS loop. So you can just choose whatever loop that you want to study and then compute this overlap and see if there is any selection rule or not. And if it satisfies the selection rule, that's a strong hint that particular Wilson loop is actually integrable boundary condition. And I think this is the simplest test of integrability for the Wilson loop, as far as I know. And maybe there might be some connection to what people studied, for example, what Krujansky studied. And he basically defined some spectral parameter what's called spectral parameter deformation, which doesn't change the expectation value of the Wilson loop at strong coupling. And there might be some relation to that. Well, there are also other possibility of using MPS representation and maybe studying other theories. Maybe we should, so far I was explaining, like this MPS works very nicely for the free theory, but I can include interaction perturbatively, but I don't know how to do it non-perturbatively. So in order to understand how to include interaction more efficiently, maybe we should study simpler theory like a 2D Yang-Mills or matrix model, or maybe like fishnet. So another interesting question is how can we see the loop equation in the matrix product state? So loop equation becomes important when you consider intersecting loops. So is there any special structure of the matrix product or this matrix when the loop intersects? Does it factorize into two, or is there any nice relation which resemble the loop equation? I think that's kind of interesting question to address. And also it might be interesting, because I started talking about the loop equation, maybe it might be interesting to combine this idea, in particular in the context of matrix model, with the bootstrap analysis of the loop equation for matrix model. So there was a very nice paper by Henry. Okay, so there are also other directions. Well, you can also try to do the classification of the bootstrap solution, which correspond to the Wilson loop. But in order to do that, we first need to know which solution to the bootstrap axiom at finite coupling corresponds to the Wilson loop. But one condition we know is that we probably need infinitely many excited boundary states. But okay, so there are many other directions that one can possibly explore. But let me just say that it's also interesting to develop systematic construction of integrable MPS for non-compact spin chain, because now we know that it's related to the classification of integrable Wilson loop. Okay, so to conclude, so this idea of like expressing Wilson loop as a matrix product state may connect various different branches of integrability in N equals 4 SIP and MILS, like integrability for the Wilson loop, Yangian for the Wilson loop, spin chain integrability, and integrability bootstrap, or a loop equation. And I think there are like many interesting questions to explore. And of course, like one goal is to use this kind of approach and then reformulate the loop equation, the gauge theory in terms of loops as Polyakov originally imagined. And once we succeeded in that, then maybe the next step is to reformulate the quantum gravity in terms of loops. Well, maybe that already exists, but anyway, it's a good place to stop.
Thank you very much for the very interesting talk. So I'm muting everyone so we can. And we have a lot of time for questions.
I might shave it. I don't know. The other day it was really bothering me. So I may just
That's the entropy of the universe.
You will not sit in your beard.
Okay, so I muted everyone again, but please ask questions and unmute yourself.
Yeah, so I would like to ask a question about this Yangian symmetric chain that you're talking about. So that's I probably missed. Is there so the Wilson loop? So yeah, I think that's the one. The Wilson loop has an unbroken Yangian symmetry. Sorry, I can't hear you, Shota.
Can you hear?
Yeah, now I can hear. So you are proposing that there is a Wilson loop spin chain which has Yangian symmetry, exact Yangian symmetry.
Yeah, only thing I'm saying is that in the spin chain, we know that there is a Yangian. Sorry, in the Wilson loop, people construct it,
which is broken by a boundary condition.
But on the other hand, on the Wilson loop, people constructed a Yangian, which is not broken.
Okay. So there are examples of spin chains with unbroken Yangian symmetry. They are long range, of course, and they are of Calogero type. So that's. Do you think there can be something similar in the case of the Wilson loop integrable model?
Yeah, maybe. Yeah, well, the only thing I'm saying is that this MPS in principle gives you some intertwiner between two integrable structures.
Okay.
So if there is unbroken symmetry on the Wilson loop side, I would expect unbroken symmetry also in the spin chain side.
Okay.
But maybe we need to make use of the fact that it's actually long range spin chain.
Mm-hmm.
I don't know. Yeah. I would expect that this only holds for a spin chain, which is really describing N equals 4 subtendencies.
Yeah. Okay, thank you.
I ask something.
Sure.
Actually, to make a link to the beginning of your lecture, which I'm not sure I find in the rest of the lecture. Can you compute something like a small variation, just loop variation of circular loop, which means inserting f mu as operator into the loop, and does it smell like integrability or not?
Okay, so I can give two answers. First answer is that maybe this inserting Q operator and acting on MPS might deform the Wilson loop in some way.
Mm-hmm.
So maybe like some combination of Q operator or something might correspond to insertion, that kind of simple insertion you're talking about.
But you insert in the middle of the loop, yes?
No, the point is that here you have like operator and the Wilson loop, and then you insert the Q operator in the middle.
Yes.
And then you act the Q operator on the Wilson loop.
Mm-hmm.
Because of this action, the Wilson loop gets deformed a little bit. Mm-hmm. Or more precisely, MPS corresponding to the Wilson loop gets deformed. Mm-hmm. So this gives you some infinitesimal deformation of the Wilson loop, which is generated by the Q function, Q operator. That's one comment. Another comment is that it's indeed an interesting question to consider something like a bulk defect two-point function. So you insert one local operator in the middle and one insertion on the Wilson loop. And we actually don't know what is the correct integrability description, especially at finite coupling. I would expect maybe something like cutting this worksheet into hexagon or things like that might work, but we actually don't know what the correct description is.
Thanks.
Can I ask a question?
Yes.
In your formulas, the Zhukovsky cut actually, if you compare your formulas to localization, then it turns out that Zhukovsky cut is actually a real cut in a sense. It's a place where eigenvalues of phi1 live. Do you have a deeper understanding of that, or can you maybe explain this in some?
Yeah. You mean, yeah, that's the connection I want to understand. And well, this is also a connection which shows up in various different places. For instance, in the work that I did with Simone Giambi, in which we computed some correlation function on the Wilson loop, I did some integral representation coming from the localization, but the integrand is given by Q function. And if you identify two representation, then you discover that the Zhukovsky cut is indeed eigenvalue cut. Mm-hmm. But yeah, the only comment I can make is that there is a nice paper by Correa and Vasquez, I think, in which they try to obtain the Magnum dispersion relation using the plane wave matrix model, like a BMN matrix model. And in some approximation, they kind of argue that eigenvalue cut basically governs the dispersion relation of magnums. But it's not very systematic approximation, but there's some heuristic argument.
Thank you.
Shota.
Yes.
Do you have an understanding how the number of bond states is related to the bond dimension?
The number of bound states is related. No.
You said it's the same, but
yeah. So
why
it's
is it the same?
Right. So it's just like observation.
Mm-hmm.
Let's say in that way. Right. So.
Can I ask a question?
Yes.
So when you mention relation to quantum spectral curve, so your answers are often written as this integral over x with some 1 minus x squared measure, and so so this and the same was in your work with Simone. So one can ask a question: what are the functions orthogonal with respect to this measure? So do you know any meaningful answer for this case of Wilson loops? It's the same measure roughly that we see from quantum spectral curve also.
Right. You mean?
So, for example, in your work with Simone, you found that you have different Q functions orthogonal with respect to this measure, and they correspond to some orthogonalization procedure for building good operators.
But this measure is also more or less the same. But you are talking about the, let's say, you are talking about tangent hyperbolic, or?
Yes, the tangent hyperbolic, and also 1 minus x squared, which you multiply.
Okay, so yeah, for that we have an answer. So you can construct you can also consider the correlation function of operator insertions on these like generating function, or more precisely speaking, the open string correlation function on the D5 ring in the probe description. And that, right, and in that case, you can also do the localization analysis and compute the correlation function using the Gram-Schmidt, and you precisely get the same measure.
I see, thanks.
Do we have more questions?
Maybe I can ask one more question. So when you take these bond states and combine together to describe this infinite dimensional matrix products, bond dimension matrix product state, or in the other case, a k-dimensional one, how do you fix the individual normalization of each term?
You mean, why don't I put like a factor of 2?
Yes, sure.
Well, but I guess like if you start from one boundary state and then construct others, I think it's more natural to just put one to other ones. But yeah.
These are sort of different boundary states, no? And you are making a linear combination of this boundary state.
Right, but okay, so I think it becomes clear if you go to this reflection picture, then you are just having some like a one boundary state and some boundary bound state. And if you want to compute the partition, sit in the partition function, you just need to sum over all possible states, including all possible boundary bound state. So from this picture, it's kind of natural to just like sum over all possible boundary bound state with weight 1, because you just need to sum over the states.
I see.
Shota,
yes.
If you differentiate the Wilson loop with respect to the, say, the coupling constant, we'll create an operator. Yes.
Yeah.
So which is this operator? Is it the identity or?
It's in the same multiplet at trace z squared.
I see. So is it possible using the boundary states to compute or to recompute the polygon Wilson loops starting from the derivative?
Yeah, it's an interesting question. Yeah, it's indeed an interesting question. Indeed, yeah, I don't have any clear answer, but it's indeed an interesting question to apply this approach, especially the weak coupling approach, for instance, to polygon by considering like a generating function of polygon Wilson loops. But yeah, at this point, I don't have much more to say.
What about other sectors, not SL2?
Yeah, yeah. Well, combining, especially like using what you did, we have well, of course, we have asymptotic formula for other sectors thanks to your work, and we can, in principle, test it indeed, but we haven't done it yet. Yeah, in particular, we are now focusing on getting some one loop data to really make sure the solution to the crossing equation that we derived is correct. But we didn't even do it for SL2 in the case of one loop. So the first thing to do is do one loop check.
Thanks.
Hi, Shota.
Yes.
Yeah, I remember in the first G function paper, there was some interpretation for the law theory. in here, can you give some nice interpretation for your load theory for the MPS?
From the string theory point of view, it's the same. It's basically like open string living on the probe D5 brane.
Is there some graph duality?
Right. Yeah, I think it is. It's basically bilocal on the worksheet. So sorry, on the Wilson loop, and it's in some sense graph dual, I think.
Okay, thank you.
Okay, are there any more questions?
I have. Shota, you mentioned the connection with the bootstrap of Penedonius and Nakaratev. But as far as I know, this bootstrap is for a massive theories.
Right.
How do we connect with in equals 4?
Right. So what I had in mind is to do some bootstrap on the worksheet. So let's say you want to study some other theory, not n equals 4. So then the worksheet theory dual to those theory wouldn't be integrable. So if you really want to understand Wilson loop in those theories, maybe we need to develop some this non-integrable form factor like bootstrap, including boundary state.
Okay, thanks.
I also have a naive question.
Okay.
Could one imagine to use this method to evaluate the expectation value of the Wilson loop in the vicinity of a defect, so that you would use all the single trace operators as a complete set of intermediate states somehow?
Yeah, that's an interesting question. So naively, it looks like a finite side cylinder with one end given by defect boundary state with the other end given by the Wilson loop boundary state. No? But finite size cylinder is at this point very hard to compute because typically in TBA, I need to send one of the lengths to be very large. But typically what you do in order to read off the 1-point function is to take this length to be very large, but maybe you can try to take this length to be very large. So it's a bit similar to like what people did for Hagedorn temperature.
Yeah, okay.
So maybe that might capture some interesting physics.
Yeah. Okay, thank you.
Any more questions for Shota? Okay, yeah, if not, I think we can thank our speaker again and thank for going for 2 hours.
Sorry for going for 2 hours.
No, it was very interesting. But it takes stamina. So thank you everyone for participating. And
do we know who the speakers next week are?
Yeah, next week we will have Ines Aniceto. She will speak about a recent paper with Michael Abbott, and we'll confirm the day because I think we're still a bit unsure about the time for next week.
Okay, do you mind if you announce it a little bit in advance? Because sometimes, yeah, thanks.
Okay, so thank you everyone. Thank you, Shota, for the very nice talk. See you all next week.
See you.
Bye.
Bye.